hear me? In the back? Yes. Okay. So I'm always nervous to talk in Silicon Valley or in the Bay Area because you guys know everything. So I'm always wondering, can I tell you something new? So I'll take that risk and I'll just tell you a couple of stories. And I usually like to start with this story. This is the common raven. Apparently it's the most intelligent bird on the planet. In the California desert, however, these ravens are undergoing a population explosion and are literally wiping out the baby tortoises. This picture is something that we're seeing for the last many decades in the California desert. There are thousands of shells of alive eaten tortoises found in the desert. Nobody has managed to record the predatory act nor understand the behavior. However, what we know is that the raven is attacking baby tortoises and that we're down to the last generation of these tortoises. If we don't do something about this, they're gone. So why is this happening? Us humans, again, messing it up. Thanks to urbanization and to a lot of garbage that we produce, the ravens are living in El Dorado and they're just not having any predators, so the number of ravens proportionally to the tortoises has exploded. It's so big that the balance that used to be a natural balance is disturbed. So if we humans ruin this, we should make it right? And two beautiful humans actually thought of something. They thought to create a techno-tortoise, meaning that they would place fake tortoises in the desert and number one, lure the ravens and record the behavior and understand what is happening. But then more importantly, they want to rewire the ravens' behavior and teach them how not to attack the tortoises. Well, how will they do that? Well, the first thing was how they make a good copy of a tortoise, a physical copy. Well, they started making it like little sculptures and painting that was painfully slow. And then, it's almost like a fine art. So it was not scalable. And then they heard about technology that I was working on, which was called Remake, now it's called Recap. It's the process of photogrammetry. You take a bunch of photos of an object with a simple camera, even with your iPhone, and the software automatically converts that into a 3D digital replica of the model. You do nothing else but taking the photos. That's all you do. And then we load it in the software and you get a 3D digital model that obviously, now that it is 3D, you can 3D print and you can touch this later, but this does look like a real tortoise to me. So does it look like a real tortoise to the ravens? So let's see. Apparently this is the most intelligent bird on the planet, yet it was trying for 20 minutes to find the body in a 3D printed shell. So it seems like we fooled them. That was the first part of the project. But now how do we teach them not to attack the tortoises? Well, Bill Boorman, who is one of the two beautiful people who has spent all his life with the tortoises, and Tim Shields, who is an entrepreneur, technologist, they're thinking now to put a little pressure sensor on each of the tortoises that when the raven attacks, it sprays a little pepper spray. It's not a pepper spray, it's like a grapefruit spray or something that the ravens really don't like, but they cannot be hurt by that. They just don't like it. And if those birds are really intelligent, at some point after 3-4 times, they'll say, I'm out of here, man, this is not for me. So this is one of the stories why I moved to technology. I was an architect for 12 years in Vienna and in London, but I realized that technology can empower small players to play the big game. Because these guys have no money, but they use free photos from their phones. They use the technology to convert those to 3D that is super affordable and easy to use. Then they use 3D printing to make physical artifacts. Then they use Arduino to make the move. And they use Kickstarter to fund the project. This is the brave new world we live in. And these are just some few of the many, many technologies that are happening now that enable many people to do something good for the world. So, as Greg said, I work for Autodesk. If you don't know anything about Autodesk, we exist for almost 30 years, and we're helping designers and engineers of any kind to create the physical world around us, to imagine, design, and make the world. So be it architects to design beautiful buildings, or civil engineers to design bridges and roads, or car designers and designers of items that we adore. I'm a Ducati rider. And then obviously designing the machines that make those beautiful items that we adore, but also in the world of media entertainment, we let artists imagine the fantasized or horrifying futures that we can imagine. So while we're working on these many types of software, we're always looking ahead. What's going to happen with the industry, with the discipline of design, with the discipline of making, given everything that is happening? And you know that a lot is happening at the moment. I mean, we pretend everything to be normal, but we're talking about, 3D printing and machine learning and infinite computing and Internet of Things, and you cannot wrap your hand around it because it's happening so fast and it's so much. So today I really wanted to talk to you about some of these trends and how we at Oculus think that they will impact the way we will be imagining, designing, and making the physical world around us. As you will see, many of them have on their own an impact on our industries, but all together converge in something much bigger. So, we are on the verge of a revolution. It's cultural, it's technological, and it's social, and it's called infinite computing. And infinite computing happens because of the confluence of three trends. One, the exponential increase of computing power that we all enjoy today. Number two, the democratized access to that power. And number three, the precipitous fall of the cost of that power. Now combine those three things with the scalability that the cloud, we know what cloud is, it's a bunch of servers somewhere in Iceland or wherever that compute a lot of things at the same time. So combine those three things with the scalability of the cloud, and what you're looking at is being able to apply infinite number of resources to solve problems that our architects or engineers, many of us are trying to solve. So let me make that more simple. Imagine you have a problem, and you apply that problem to one computer and say, solve this problem. The computer will take, let's say, 10,000 seconds to solve the problem, and it will cost 16 cents. I keep on changing that number to lower and lower, and I just stop changing the slide because it's just getting cheaper. So now imagine, instead of giving the problem to one computer that will solve it in 10,000 seconds for 16 cents, we can give the same problem to 10,000 computers at the same time. And they can solve the problem in 1 second for the same amount of money. The ability to apply infinitely more resources at no additional cost is first in human history, and it will definitely change the way we do pretty much everything in life. So how will it affect design? Well, let's see how design used to work before we had infinite computing. As designers, we explicitly were telling the tools what we want to do. Oh, I'm designing a chair, I'm explicitly drawing something, right? And then I, the designer, again, decide when is the right time in the design to apply simulation to see if the chair will break or fall or it will function or not. So if I were to design this car seat, what I would usually do is I design it, and now I say simulate. And I see there is a red zone that usually means it will break there, it's too thin. So I'm redesigning and making that thicker. And then I send again to simulation. But what I didn't tell you is that the simulation each time is about 6 to 7 hours. It can be 10 hours. So you wait to do it again. And then again, you get something, oh, it's slightly better. And then you keep on going. You propose and you dispose. You propose and dispose. And finally, you arrive to something that just passed the simulation. It's better, but is it optimal? No, it's not. It's just something better. So forget that. Imagine a world in which instead of running one simulation at a time, you can using the cloud, run thousands of simulations at the same time concurrently. And that is exactly what is the value of infinite computing, that it enables you to basically extrapolate, mash up, and mix up infinite number of designs at the same time. Welcome to what we call generative design. So basically, generative design takes goals defined by designers, defined by engineers. They can be cost as a goal, material as a goal, style as a goal, basically anything that you can describe a problem with. And it takes those goals and then applies smart algorithms, often based on evolutionary patterns in nature. And it just opens the design space and looks at all possible solutions within your goals to solve that problem. So in the future, instead of just designing explicitly and using simulation after we design to check if it's a good design, or even using simulation during design, which is super useful as a feedback, we will be using simulation to discover design. So here we just said, I want a chair, I want a surface on which I sit. It has to hold 50 kilos or 70 kilos of person, etc. And the computer just goes to thousands and thousands of options within the material that we picked, within the cost that we decided, etc. Evidently, it will result in something that will be less of a cost, it will have less material consumption, product weight, and less development time. But it's not just about the fact that it will be more optimized. It's about the fact that we're designing in a completely new way. And about the fact that it arrives to designs that we would have probably never come up ourselves. So this is Lightning motorcycles. It started with a great idea of somebody who really loved motorcycles and just wanted to make a fast motorcycle. They managed today to do the world's fastest production motorcycle. Oh, and it so just happens that it is electrical. It's the fastest motorcycle in the world. Now, as they know, the thing about being a winner is to stay a winner. And staying a winner means you do not accept and live in your glory, but you're constantly trying to improve. In this case, they want to be even faster. So how do they do that? Well, usually speed is connected with weight. If the motorcycle is lighter, it will be faster. Well, the swing arm is one part of the motorcycle that is usually quite heavy. And it should be because it has a lot of force going on this. So they were looking how to optimize the shape to use less material, but still be strong enough to hold the wheel, to hold the frame, etc. So they applied on the part that they designed. This should be running, yeah. They applied generative technique to remove and remove and remove more and more material and try to find a shape that will still hold and be just as strong, but use as little material as possible. Obviously, this helped with the speed of the motorcycle. But look at this. One of these is a cat pelvis, one of this is a dog pelvis, and one of this is what the computer designed. Evidently, it looks like what nature would have done. And it's not even symmetrical because the motor is on the one side and the brakes are on the one side, etc. So when we say evolutionary patterns, what does nature do? It always uses the least possible material for the highest possible performance. And that's exactly what these algorithms are trying to do. But this was, they take their design and then they just use generative algorithms to reduce the material, which we call optimization. The more interesting approach is to not at all take a design, which was in this case this, but just take the constraints. So what I say here is, I'll be attached here and here. Here there'll be a big force from above. Here will be a wind force from the side, and let the computer design. And that's exactly what's happening. This is why I told a couple of people, majority of the objects you see on the table have not been designed by a human being. They've been designed by the computer, by the algorithms that are, instead of the traditional way, I think of something and then I reduce my decisions until I make that. Here, generative design opens the design space. It looks at all possible options. And then you as a human decide which criteria were you most interested in. Oh, this will be more expensive, but it looks cooler. Or this is cheaper, but then it sucks on this side. So you understand the trade-offs, and as a human, then you continue. And this is the design that they came up with. Now, some of you are designers, and you'll say, well, yeah, it's smart, but I'm not sure I like that shape. And our eyes are used to sharp edges and man-made things and designs, and this feels uncomfortable because it looks organic. So we're already looking at that, and there will be ways in which you can take that design, that computation as a beginning, and then continue designing and developing in your way, but not losing the smartness of what the algorithms gave you. For years, we've been working with Airbus. Airbus wants to basically make flying more affordable, better for the environment, and more experiential. Imagine if you were flying in this airplane. It's a little bit nicer than that claustrophobic, slightly stinky cabins, right? So the first project that we started to work with them was about this partition. This partition is very heavy. It's solid steel, and it needs to hold the stewardess seat. So anything that is less weight on an airplane means less pollution, and means less using of gas, and means we pay less for the tickets because it uses more gas, right? So we applied the same type of algorithms to see what is the minimum material in design that we can still make this partition not trade off on the safety of the stewardess seat, etc. So we arrived at a bunch of solutions, and from something that was solid and heavy and weighed 65 kilos, this is now the new partition, and you are already flying in airplanes that is now having this partition. It has 45% reduction in weight, and it uses a third of the material, and it's stronger than the one before, which is kind of crazy. And that's this one. Now we continued with Airbus, and now we're looking at seat frames. Now, this is not using technology for the sake of technology. This is using because it has actual real implications. In this case, we're talking about, I have to read this because I'm not good at remembering numbers. We're reducing weight up to half a ton on a bigger airplane just by changing the seats from being solid steel to this generatively designed 3D printed frame. It will use 200 tons annual carbon emission less and $200 million in saving. In this case, I will talk about that later, this was not 3D printed. It was first 3D printed, but then the 3D print was used in a lost wax casting process, and it was metal casted. But these are serious numbers. This is really about cost, about material, about the environment, about the ecology. Now here is something very interesting. Only when we 3D printed the partition did we realize how difficult was it for us to understand it. We couldn't see where the print will fail, but the computer could. We could hold it in our hands, but we could not hold it in our heads. This is too complex. And this is what's happening new now. Our designs, our own designs, start to become inscrutable. Earlier they were inspectable, they were understandable. Now they're inscrutable. And we will need some help that goes beyond our 16 bits per second to solve those problems. Now you'll say, well, that's all good for mechanical engineering and design because it's physical artifact. What about generative design and architecture? How can we apply this approach of setting a goal and the computer helps me? So we took that challenge as we were just moving into a new building in Mars in Toronto, in the Mars complex. And what my colleagues did was the following. They wanted to use generative design to find the most optimal solution space for everybody who works there. So the first thing they did was interview everybody. Oh great, you like to sit next to a window, but close to the kitchen because you drink a lot of coffee and stuff. And you like to be in a corner, you don't want people to bother you, you're a programmer, nothing light, no light for me and stuff. So basically, they tried to interview everybody and understand what are their preferences if they could choose. Now, I'm an architect. I would have a problem already in a family with 4 people to design a house that is perfect for all their needs, let alone 300 people. Right? We cannot process that. Our brains cannot compute so many things at the same time. So we interviewed them, and then we defined goals. The slide is a little bit chopped off, but basically, these were the adjacency preferences, desk preference, productivity, daylight, all of these things that people were asked about. And then we applied the hard constraints, which is the building already existed, so we knew where the walls are, where the stairs are, where the kitchen is. And then we let go. We let the computer think about it. What you're seeing here is the magic of automation. We don't like the word automation because it always means something, non-creative or something. It's the wrong word. What the computer is doing here is literally looking at all parameters for all 300 people and trying to find the entire solution space. All of these dots are possible solutions, but in the one of the things will suffer, in the other another. But for the first time as a designer, I understand the trade-offs, and that is the value of this. It's not that I let the computer design. I let the computer inform me about the many decisions that I neither can compute, nor can I so quickly understand. So we arrived to a solution that, at the moment, our colleagues are still happy about, but if they're not, we will run another way, or if we get a new batch of people, and we can reconfigure the space, etc. So our traditional design tools earlier we're very passively awaiting for instruction. I draw a wall, I draw a wall. I make a floor, I make a floor. This is a completely different approach. Here, instead of being directive to the software is adaptive to us. It starts to understand what we're trying to do, and it starts to even be proactive about informing us what we need to know when we do something. So generative design, if you remember anything, is it starts with goals and constraints. It opens the design space, and it's not just about optimization. It really helps you augment your creativity because it offers you solutions of something that was unexpected, unknown, that you would not have thought of. Now, when we design all of these crazy shapes with generative design, there is one big trouble. No traditional machine can actually produce them. You can have 6-axis machine, the most expensive one. If there are too many holes, like in this design, or it's too organic, machines can simply not do it. The only reason why they can do it today is because we have made additive manufacturing, or what we call 3D printing popularly, possible and more affordable than ever. So you probably all know what 3D printing is. Basically, it's an additive manufacturing method, unlike subtractive, where you take a block of material and you carve out, cut until you arrive to the shape you want. This is the opposite. It only uses as much material as you need. It goes exactly like a printer at home, but instead of depositing ink, it deposits material, one layer, and then it goes up, another layer, it goes up, another layer, it goes up, and then it prints the shape. This is literally how it looks like. Now, while everybody knows this part, many people are missing a couple of really key things why 3D printing is really interesting. Number one, a 3D printer cannot care less if you're printing a box or if you're printing some of these crazy shapes. For the printer, it's the same thing. It goes left and right. It just follows the recipe that you gave to the printer by having created a 3D model that was sliced in millions of slices, but you don't know that, and the printer is just going slice by slice and depositing material. So we get complexity for free, which is quite exciting because we were so limited to do some, Euclidean shapes until now. The other thing is that printers can print in many materials. Up to now, we were comfortable with about 85 types of materials, but the future of 3D printing will be interesting when we invent new types of materials. Another thing about 3D printing is that it can print a whole mechanism in one go. This particular mechanism that I brought for you to see, this is usually made out of 50 pieces, but this is printed in one go. Nobody was putting pieces together. It was, if you designed it to move and you send it to the printer, it will be printed in one go like this. Now just imagine what will that mean for the future of manufacturing. That means that we will not have assembly lines. We will not have kids in China or in India assembling stuff for us. This will be printed in one go. And as materials change, we can also print multiple materials in the same printer at the same time. And those materials can be hard and soft, transparent and matte. So we're talking about really totally new ways to fabricate. So in Autodesk, if all of this is happening, what are we doing? We not only have design tools that help you, software that helps you convert or prepare any model for 3D printing, because it's not just as easy as, oh, I designed this so they can send it to printer. Printers are super finicky and they don't like double curvature and inverted normals and all the things that you don't need to know about. But we have software that can do that. That software also can simulate the print before you print it. If this is a metal print, this costs a lot of money. So you better see that it will work before you print it. And real-time simulation is based on physics, based on gravity, on everything that is in the physical world, will inform you if it will fail or work. But we don't know how to design to leverage the power of 3D printing. If the printer can print every single droplet in different color and material, how do I design that? We usually design, a box and then this and that, but we don't design droplets, the voxels. So now we have some people in Autodesk who are actually looking at creating new voxel-based tools where you create some shape, but then if you're seeing pink color, that is where every droplet is actually a different material, a different density. So on the desk you will see there is a prosthetic leg. The leg is rubbery, and it's stronger in the back where the heel is, and it's softer in the front. You can do all of that in the same one machine. And what's crazy is that the same machine can at the same time print a turtle, a razor, a gun, whatever. We don't have any more molds and casts. It just follows a recipe and it prints. That's the big thing. You don't need to do tooling, because that's what makes manufacturing expensive. This is why you cannot get every chair to fit everybody's butt, but you have to sit on the same chair, because in order to do that, we have to understand, we have to have machine be able easily to produce different things, and today that was not the case. So with tools like that, we can create one object that has very different densities, different colors, different materials. We can have materials with non-linear behavior. Now imagine you start mixing carbon fibers and optics and this and that. You can start making these materials sensible, so they know where you touch. They can sense the environment for temperature, for stuff. This is going really science fiction where it could go. But if we come back to the planet Earth, this is also something that we can do today. Like this beautiful table design from Sawako Kaijima, where he used this tool to design something and be printed in one go, but you see those little strains. There is no way to do that today. There simply isn't, unless you have tools and printers like that. Now the bad news, this is all the good news about 3D printing. The bad news is that it's still small scale, slow, and expensive. So we had a research in-house to just see, can we parallelize multiple heads so that the printing starts becoming faster and it prints bigger things, so we can start printing buildings or airplane wings or really bigger items. And here it's really about parallelization. But what's more interesting is that this system that we built does not have to be just additive, just 3D printing. You can combine a machining head with a printing head and combine additive and subtractive manufacturing, because we know that there is no future in which it's only additive or only machining, meaning cutting, milling, etc. But the future for making designs, making things, is the combination between the two. And for example, you know, the Airbus, after making the partition, they realized, okay, if we 3D print this, it's not going to, it's better than before, but it's not that optimal. Now they know that a combination of using the print in a lost wax casting process, so basically you print something, you cover it with plaster, you burn it, the print melts, and then you pour bronze or metal in it. That would be a much better way to do that. And that is, for example, what you see here. This was actually porcelain and then burned. So this might sound cheesy, but in the future, from smallest scale to biggest scale, we'll be able to print lots of things. We can print nanoscale, which is DNA. We can print organs, and Organov is already working on printing kidneys, printing ear pieces. This is already used in some advanced hospitals where you can easily scan part of the scalp or whatever you have as damage and then print in titanium in this case. We've been working with a company called Unique that wanted to make unique prosthetic covers for amputees that are not only unique for their body but also unique in the style. We can obviously print food, and as you will see later, you can easily capture with photos the face of your boyfriend and then print him in chocolate and eat him. And new types of materials that can behave differently. This amazing woman is a friend of mine, Iris van Herpen. She is one of the top fashion designers in the world. She was one of the first ones to start using printing to create new materials or new crazy shapes. They're the first 3D printed cars by Local Motors. The first printed houses on planet Earth or planet Mars. Actually, this was Professor Koshnevitz years ago talking about the fact that it's all the same thing. You have a nozzle that extrudes material, and it doesn't matter which scale, it's still the same thing. Students of his started to actually build these houses, low cost houses in low-income houses in China. They can be erected in 10 hours, and they cost $5,000. And we're starting to see robotics that we should be running, but it doesn't matter, that is starting to look at 3D printing on building level. Now, another trend that we're talking a lot about is sensors. We live in a world of sensors, and it is easier than ever to capture the real world and digitize it and bring it in a computer. The first sensors were laser scanners, and it doesn't matter if they were put on a tripod or on a drone or on a copter. What they were doing was shooting laser beams in space and then rotating. Every time they shoot a laser beam, it hits the first surface it finds, and it sends back that signal to the laser, and then it gathers positions of points, XYZ coordinates in space. And that is how we're digitizing the environment. In the last couple of years, we're seeing a lot of devices that are from Tangles and Kinects and white light scanners and blue light scanners, structure scanners. All of these devices have some kind of a sensor that when you swipe over, you can digitize what you're seeing. And the third one was made with the process of photogrammetry, which is for me the most interesting because all of us can do it. You just take a bunch of photos of whatever object or person you want or of an environment, and you give it to the software, and it creates automatically a 3D digital model. Could you have modeled this 3D digital model? Of course, but you needed to know Max and Maya and spend probably weeks of modeling this versus, and it would never be the copy or the replica of that particular object. It would be an interpretation when you model it. This one is a real digital copy of that object. And if that was not enough, we also live in the world of drones, so you can put all of these sensors on a drone and do the same. So just to give you a sense how fast technology has improved, this is only a couple of years ago in AutoCAD, laser scanned environment, and it looked like a bunch of bees, a swarm of bees in space. You have no idea what's going on. It's black, and it was killing AutoCAD. It was once you put the laser cutter, nothing, the laser scan, nothing worked. So that same scan now looks like this. It literally looks like the environment itself. You didn't need to model anything. You're basically in the space, and as you can see, it's also super fast. So architects, engineers are using this method now to quickly capture existing environments instead of remodeling them in software and then planning what they're doing inside, and be it for factory retrofit, etc. And the software automatically connects the scans in one scene and then starts to behave really smart. These are all just points, but it knows that it's a cylinder because the points are arranged in a way that the software knows it's a cylinder, and then it can measure the radius of the cylinder, etc., etc. And as I said, the drones, you can put basically any of these scanners, but today you can just put a camera, fly over. The drones today are so easy to fly. You can literally walk and it follows you like a dog, and it scans everything, and you just upload the photos and you get a 3D model of the environment. And you can use it for many things, either when you start a construction site to plan the digging or the plan access, etc., to inspect dams so they don't crack and we have the dam problem, etc. But the same technologies are not only interesting when you create something new, they can also help us digitize our heritage, preserve our heritage, because thanks to tsunamis and earthquakes and terrorist attacks and wars, we start to massively lose our history. And one way to at least create an archive for our future generations is to capture what we have. When we have money, we restore the things. But today, with this technology and then combined with AR, VR, we can actually experience spaces without ever going there, because not all of us have the luxury of traveling around the world and seeing everything. And we have the government in Rajasthan. If you've never been in Rajasthan, I strongly recommend it. It's unbelievable. Jaipur has all these Aladdin, 1001 night palaces that they're just falling apart, and they don't have money to restore them. But now they're capturing everything. They have digital replicas. They think that this could be also an interesting way to do a new way of tourism. They can also sell these models to media entertainment companies for making movies. But they also use this in planning of smart cities, where they can sensorize everything and see if the structures are holding up well or not. Using the same set of technologies, Smithsonian, who is the biggest collection of museums in the world and have about 150 million objects, was thinking to digitize. Why? Because if you go to museums, you see only 1% of their collection. They simply don't have enough space to show it. But obviously they were also interested to get out those things from their archives, and also interest the generations of youngsters who only stare at computer screens and think that museums are these boring, dusty institutions, and they're not interested to go there. So they believe that if we put those collections online, that and connect them with some stories, that kids will be more interested. And that is exactly what we started to do. We built for them a WebGL-based online explorer, in which all of these artifacts are not only as beautiful as in real life, but you can actually augment them and see something that you couldn't see with your bare eyes if you stood in front of that statue, which was the case with this Buddha. It's a cosmic Buddha. The curator could not read the relief, which is the story of Buddha, because it was already beaten up by time. But once digitized, we could deepen the relief and read more what was going on. This is a tool for curators to tell their stories in a 21st century way. This is a tool for teachers. I teach about the mammoths. I can tell the kids, hey, open the mammoth and tell me how tall is the leg, etc. Or we can just have fun and make some art or stickers to a t-shirt or anything. This is a new experiential way for kids to learn. One of the last projects we did with the Smithsonian was the digitization of the legendary Apollo 11 that is kept so tightly in a plexiglass. Nobody can see inside, nobody can touch, not even the curators there go inside. So it was going to be open to be sent for another exhibition, and we said, this is the time to digitize it. So we digitized the heck out of this thing. We used structured light scanners and laser scanners and photography because we knew this is our chance. And we managed to create a beautiful 3D digital replica of the Apollo that all of you can enjoy now. If you go to the Smithsonian Explorer, you can put VR set. You can also literally be inside and sit in it just like the astronauts. Actually, Michael Collins was the astronaut who did stay in the Apollo capsule while Neil Armstrong and Buzz were on the moon, and we gave him to experience how the kids today imagine him being there. So these technologies are really allowing us to cross geography, to cross time, to connect experiences. Another use of the same technology is for another type of education. Professor Saunders from Penn Design is teaching Baroque architecture, and if you're like me who studied architecture, this is how we learned about Baroque architecture. It's from sections and floor plans, and you literally didn't learn anything. Baroque is so complicated because it's a combination of sculpture, painting, and architecture, and it's not easily describable in sections and floor plans. So what he decided to do is he went to Italy, selected 14, 15 of the most iconic Italian Baroque churches with his students, and they scanned them from inside, and they created these unbelievably beautiful replicas and a website where you can enjoy them. These, by the way, are actually, if you imagine a church and you fill it up with water and then you freeze the water and then you break the church, this is what remains. This is the solidified interior. But it was unbelievable for the students. I mean, the print, obviously the digital versions, you're in the church so you can experience, so the students could really learn, could close up to any of the sculptures to understand everything. And the idea for them was to understand the rules of Baroque architecture and reverse engineer that and start creating new Baroque architecture with that new language that they learned about. These technologies also allow us collectively to do something good. These are the Buddhas of Bamiyan, the story of the Buddhas of Bamiyan. They were colossal statues carved in stone at about 4th or 5th century. And sadly in 2001, they were destroyed forever by Taliban after being declared as idolatry. I don't know how to spell it. This is really very sad for the conservation community, for the people living there, because all that remained was this. And we were just at that time working on the photogrammetric tool, so one of my colleagues said, what if we start to collect all the photos on the web from tourists who have been throughout decades going there and taking pictures of these Bamiyan Buddhas and try to reconstruct it. So basically, we downloaded everybody's photos who was generous enough to just post it online, and some were analog photos, these were not even digital photos. But we managed to combine a bunch of photos and recreate in 3D something that does not exist anymore. Was this perfect? No. But this was, half of the photos were analog, and they were not even shot at the same time and climate, etc. Imagine with the phones today, with the sensors that you have, this will be a joke. And we all can participate in saving our environment, in protecting, preserving, etc. Because in the future, we can digitize entire cities, we can digitize our lives, see ourselves as we were, the way we were as we were kids, etc. Now, sensors are much smarter than just capturing geometry. They can capture pretty much anything. So, to explore the power of Internet of Things, because that's what we're talking about, putting sensor of things to measure something, it can be anything. We sensorized almost our entire building in Toronto, and the idea was to empower the building to become smart, to be responsive, to get a voice, to be alive, to tell us architects, did we suck when they designed it, or did we design it well? And what about the people inside? Why are they turning on air conditioning and opening the window? So, you know, very often you have cold and hot call at the same time. Somebody's freezing, somebody's hot, and nobody knows what's going on. So now we have a live feedback by the building that we know at all times what's going on. And it can be measuring any types of energy or wind or occupancy or humidity or anything. So we built this, the research team built this Project Dasher that is basically an interactive building performance visualization and management tool that combines the world of sensors with cloud-based analytics and real-time shows you the performance of the building and what's going on with the people inside as well. This is really a convergence of a BIM design with real-time performance data. And Internet of Things means just that. It can connect and make sense between physical things, physical to physical, physical to software, software to software, and we start to understand our actions and be able to correct our behavior, correct our designs. We just opened the advanced manufacturing facility in the UK, and we're not just measuring the spaces, but we now are sensorizing the robots themselves, and we can basically at all times know the behavior of the robots, their productivity, if they're failing, etc. We'll be just living in a world of data. Now, I mentioned the magic word robot, and there is no talking about future without talking about robots. But robots are really nothing new, in spite of the fact that everybody's talking about them now. Robots are those things that make things in a factory. Only they are at the moment quite dumb, because they could do just about anything, but we have put them in an environment where they just do one thing. Why is that? The bottleneck with robots is that the interfaces to program the robots today are so complex, and they take so much time that if you needed to reprogram this assembly line to do slightly something better because you want to improve on the design, it will be done for about 2 years, because only some experts know how to program these robots. Well, that's really not what robots are about. And this is by the way, one of the reasons why robots are not yet used massively in architecture, or why we're not offering people personalized objects, because if I could reprogram the robot quickly, every chair could be different, every tool could be improved. But because it's difficult, we keep on producing the same thing, right? The other problem about robots today is that everything about them is hard-coded. They have to be here and fixed. The object that they work with has to be here and fixed, and they have to be in a protective environment, because if you go inside, you might become a prey of the robot, because they don't know that you're there. Or if somebody puts that car chassis there just a little bit to the left, everything breaks down, because they have been hard-coded for a very constrained, fixed environment. So, nonetheless, we think that can be improved. We can make robots, both the interaction and the language that we talk with the robots, much easier, but also the way to teach them and program them, or let them learn how to do a certain task. So our previous CEO was an amazing guy who was a maker, and there was no book. His name is Carl Bass, and he's like, come on people, don't tell me that I have to go to CAD to draw a square or a rectangle only to tell a robot to cut a rectangle on the wall. So in this case, what we did is we took a little robot, we equipped it with web camera and the projector and the router, and using natural language processing, we taught him how to understand what we're talking about. And we say, okay, cut that shape that they just pointed the corners with, and the robot will do that. That's how we actually want this to work, not to have programmers to program all of this. So now, here's to a little bit more advanced robots. This is a big one. If you come to Pier 9 and visit us, it's a scarily big robot that is very heavy. So we created a metal 3D printer out of this robot. How did we do that? This is, by the way, his name is Ash. We basically gave him eyes to see and hands to do, and it started to basically weld or 3D print metal. In this case, is the chair that I showed you before. So great, we made a 3D printer out of robot. That's not the interesting story here. What's interesting is that this robot sees at all time what he's doing, and understanding what he's supposed to do. If there is a mistake, he corrects it. If something is leaking or something, he will go and repair that. There is a feedback loop on what the robot is doing, and it's relearning from that, so that it is correcting and self-improving as it is doing it. And that is where these machines are going. This is the chair, by the way, that it was doing it. So while we build more capability in Ash, we also want to build flexibility into the ways we work with Ash. And we created this virtual environment. It's a full-scale virtual environment in which we can step into the robot's world, and we can control him just by controlling through the VR. This allows us to be nowhere close to the sparkling metal, but also to understand before we start working with the robot, will it hit something? Will it be able to reach somewhere? So this is the way we're going to make these robots work much smarter and much better with us. Now, this is another project, and this one is very interesting. This is another robot that we call Bishop, and we introduced Bishop to the disorderly world of the Lego. And we wanted Bishop to understand Lego bricks and to pick them up and to assemble them. Now, we started to teach him, and when I say teaching, it's basically from previous experience. He just gets better and better. So we were seeing a progress, but it will take us another 3 lives until this robot actually learns how to do something that a child picks up in 10 minutes, right? So we had to speed up the learning. So what we did was, we created an artificial world for the robot, and using simulation, what we showed the robot is how, we showed him rendered bricks with the real physics, etc. So we disengaged the robot learning from the physical world, and he started just to learn in the real world, because otherwise we need to get about 1,000 robots, physical robots doing stuff. So he started to crank hours and hours. And by separating the physical environment from the learning environment, we basically managed to compress time. Because now it was doing in digital time, and we managed to do unbelievably a lot of learning in a very short period of time. So now this robot is super smart, understands the bricks, understands the length, understands where is the best point to touch him, and starts building whatever shape we did. The last 2 projects that I mentioned are all about machine learning. We did not program these robots. We taught them to learn themselves, and all we told them is the task we want to achieve. And machine learning is the big buzzword. It's not just a buzzword. This is coming to us like an avalanche, and it's going to change pretty much anything that we're doing. Why do we use machine learning? Because there are problems in the world that we simply don't know how to code, or are too complicated to code. Machine learning is when you type a word in Google and it auto-completes, when Netflix offers you a movie that you might like, or Amazon a book that you might like. This is all machine learning systems. They learn from your previous data, and they know more and more about what you're doing. But the best example and most advanced is self-driving cars. Self-driving cars cannot be programmed with if-then conditions. In order to program with if this happens, you do that, you have to understand all possible conditions that the driving car will get into. How would you ever do that? How would you know when a dog comes out, when an accident happens, when there is a flood, when... These are absolutely unimaginable problems for us to solve with programming. But with machine learning, if we train the car by saying, if it's something movable, then probably it's a being, human or animal. Try not to hit it. If you have to hit something, go for this and this. So you just train the balls. It's really about understanding the philosophy of driving rather than learning a recipe that will stupidly follow. And we have to admit, self-driving cars are driving better than us. They're not putting makeup during driving, and they're not phoning and messaging and being angry about the husband or the wife or anything. We are failing beings, and if a machine can do something better than us, it better let the machine do something better than us. So in our world, in Autodesk, this introduced many interesting things. The first project we did for our customers was something that we called BIM 360, IQ, and we were looking at construction sites. If any one of you have worked on a construction site, you don't want to have the life of a superintendent, because the guy wakes up in the morning and he just hears that there are about 1,000 issues that he has to deal with. And he has no idea which of those issues are important, urgent, deadly, or just some cosmetic stuff. He has to use his brain, his experience, anything humane to figure out how to deal with these issues that were reported. So we built a tool that takes about 24 million digital documents from previous construction sites, because now we leave digital trails in the cloud. We're putting stuff in the cloud. We could use those documents, and the system learned from those previous construction sites which issues were problem, which issues could be postponed. Water issues, you better lift it up in the list. And every morning when the superintendent wakes up and goes on a site, he gets a list with already prioritized issues, and it tells him, you have 5 really important things today. This, if you can make them, these other 3, okay. This, you can ignore them. So it's almost like an assistant who knows what he cares about and proactively tells him about that. This system can also tell you if a subcontractor had a poor record on previous projects. Wouldn't you want to know that? Of course you would, but you don't today. Well, now that everything has digital trails, that experience can also get recorded, and you would think twice if you hire somebody who had that experience. So instead of looking at the past, these tools are now proactively looking in the future and helping us as assistants how to do something. So we are now also funding lots of other companies. So we have we're partnering with a company called SmartVid that are using now the photogrammetric method or photography on a site and start to apply computer vision to understand problems that might occur. If under a window, the color of whatever material is underneath, here's some darker patch, it probably is water, so it reports it. Or if it notices that somebody is on a certain height and there is no railing, it reports it as a safety issue. So just by real-time monitoring and being trained on understanding situations and experiences, it can proactively help us. So what does all this mean for creativity? Will computers ever learn on their own to be creative? Well, if you ever heard, there was a movie that was written, the script was written by artificial intelligence and directed by. This movie was, number one, very intense. It was hilarious, and it was absolutely unwatchable. And if you haven't, please watch it. But the company behind is actually a very serious film production company. They wanted to do this test, but what they're really doing is they use machine learning to predict if a movie will hit the box office or not, if a script will make it or not. There are, based on historic data, there is possibility to actually apply machine learning to that. But we also probably need to redefine what creativity means, because in Oxford or Webster Dictionary, probably creativity is finding new solutions for old problems, or, well, it seems like computers are kind of doing that already. So we should probably let go of that word that we think we have monopoly on and agree that computers can also be creative. But all jokes aside, there are already some really interesting projects, some music projects, some projects that are showing that this is not that impossible to imagine. One that I'm very impressed about was the Next Rembrandt project. You can find it on YouTube. If you have not seen it, you absolutely must do it. So this was a project at J. Walter Thompson, Amsterdam. So what humans wanted to teach the computer is to understand how Rembrandt was painting. So basically, they fed the deep network model with a bunch of paintings from Rembrandt, and it started to find patterns on the stroke of a brush. How was an eye painted? What were the proportions? What was the distance between the noses? How was the skin painted? If a guy was a drunk, how was his pink color painted? How was hair painted? They were also looking at the height information of the existing painting. And after training for 18 months together with the gathering of the data, they managed to recreate a Rembrandt painting that was never built before by telling the computer, I want a male, 30 years old, and just paint. Curators could not tell that this was not painted by Rembrandt. And the painting was 3D printed with all the layers of the oil, etc. This is amazing. And all the computer did was just receive historic data about a bunch of paintings and just analyze the paintings, and that's what neural nets do. They start to find patterns, they start to create the intelligence. So how I always say for machine learning, in math, you have data, you have formula, and then you get data. So A plus B is C, you have the C. In machine learning, you have the C, and you're trying to find the formula. You have the data, and you're trying to find how was all this data, what were the rules to create the data. And this is really fascinating. So what is a Rembrandt in the world of the design? How can we imagine that maybe one way we can design in the future? So this is something that we're just working on at the moment, and you're the first people to ever show this to. Imagine I'm designing a chair. Why would I always start from zero? Why don't I say, hey, computer, show me a chair. I want to design a chair. And it shows me a bunch of chairs. I say, oh, I am designing a hotel chair, so I pick some. Then, given some constraints, I'm telling with natural language to do some variations. Then, these are all the variations that the computer will offer given the two selected types. I can say interpolate between these two shapes because I'm not sure. I like this, but I like that as well, and I'm kind of not sure. I'm literally just, instead of me modeling this for thousands of hours, it will just help me do it. So then, this is my choice. I'm looking at it, the legs are not necessarily what I want. Why don't you give me some other types of legs? This is easy. In the design world at the moment, we use so much time with software to design things. We spend time on the stuff that is not necessarily what we want to do. We just want a visualization of our idea. Now I can say make it taller, make it for a taller person, etc. But I still have my ways to sketch over and say, follow this pattern. Or, oh, I like that fashion. Why don't you make it in that style? Or I submit a couple of other inspirational images and say, make a collection within this style. All of these things that I just showed in the last 1 minute would have taken about, you're a designer, probably a couple of months to just physically do in a software because nothing is automated. So don't be scared of automation. This is not the computer designing for you. But why would you always start from zero? Wouldn't you want, instead of UV mapping of the material and looking straight, etc., that you just do what you do? You're creative, you have ideas, you want to function, and you just communicate to an assistant who listens to you and who knows much more than you. And that's the idea. All of these projects that I showed you are possible because today we have digital data. We're leaving digital trails everywhere after we do something, be it on Facebook, on LinkedIn, be it in a bank, in the hospital. Our lives are all digital trails. And what machine learning does is takes that data and converts it into insights so that we can do whatever we do with much better knowledge and insight into that amount of data. So we started with infinite computing. I'll finish with the same. So if infinite computing didn't happen and we're still in the old world, your designs will be just contained in a box, just like our software. We'll be still selling you software that will be publishing once a year, that you will have to upgrade, and that software will be basically a tool that you have to direct. It's rigid, it's inspectable, it's conditional, it's conform, it's based on calculations, and it's based on recipes. Not very exciting. With the infinite computing world, all of that transforms into a process that is much more adaptive, that is fluid. The designs are inscrutable, but we get so much more insight about what we're doing. It helps us with something that was intuition, now based on facts and details. So the tools will be capable of representing and comprehending what we design. They will behave as smart assistants who have worked with us and who gather all the knowledge in the world and offer it to you whenever you need it. So when we talk about will the robots take our jobs, will the machines win over us, it's not about humans versus machines, because remember, we made those machines. We make those machines. It's really about bringing the best of each other together. So lots of the things I showed today are really early experiments. Some of them are dreams, some of them are actually software that we have early prototypes of. But that's how innovation happens. You need open-mindedness, you need fantasizing, you need people like us to just propose tools, and we need people like you to be embracing the unknown, because we don't know. And that's that. Thanks so much. And by the way, we're all local. We're on One Market, and we have a beautiful gallery. All of these things that I talked about, and there is so much more, are each of them at least an hour presentation themselves. I was really running very fast from generative to additive to sensors to robotic to machine learning. There is a lot around AR, VR. Come and see, we have beautiful stories to tell you. We also have a facility on Pier 9, that is our technology center, where we have 3D printers and laser cutters and water jets and CNC machines, and we're literally making all of these things that we're showing, because we learned as Autodesk it was not enough to just serve the design part, but we really have to understand the physical making of things.